Hi all, I welcome you all to the next lecture. I am Professor Ravi Kumar, Assistant Professor, School of Mechanical Engineering, Shastra, deemed to be University, Tanjore. So today I am going to discuss about basically three topics. First is what is the importance of pressure coefficient in finding out the aerodynamic characteristics of any body. Second, we are going to see how to calculate lift and drag over any body moving through the air. Third topic, we will see what are the different resistance an airfoil is going to experience while it's moving through the air. So what are different types of drags that will be discussed. With that, I will conclude the today's discussion. So let's start with pressure coefficient, right? Usually we have seen whenever any object moves through the air, if we look at the surface of the object, pressure will not be uniform, right, when it's traveling through the air. So if we are considering only static pressure for our measurement, it will be very difficult to exactly predict at different locations what is happening. So instead of dealing with the total magnitude of pressure, it is a good practice to deal with a non-dimensional form of pressure difference with a free stream pressures. Usually the free stream airflow pressure be considered as a datum, right, and with respect to that we measure the pressure on the surface of the object which is moving through the air. So it is a very convenient way to define the pressure difference in non-dimensional form, that is known as pressure coefficient. So pressure coefficient is a very important term, right, when we are finding out when we are going to draw the pressure distribution around any object. So how to define a pressure coefficient? Pressure coefficient nothing but it is the ratio of pressure dynamic pressure by dynamic pressure, or you can say pressure difference between the surface of the object and free stream divided by the same magnitude corresponding to the kinetic energy. So as per the Bernoulli's principle, we know the dynamic pressure is given as we used to say delta P. Any pressure difference is given as half rho infinity V infinity square, and this dynamic pressure is nothing but P is the pressure on the surface minus P at free stream. So P infinity is our basically our free stream pressure, and V infinity is the free stream velocity, and rho infinity is the free stream air density. So this is the dynamic pressure. If I divide this dynamic pressure P by P infinity by the same quantity, I will get a non-dimensional pressure that is called coefficient of pressure. So coefficient of pressure is nothing but it is defined as Cp is equal to P minus P infinity divided by half rho infinity V infinity square. This term is known as coefficient of pressure. Why it is needed, right? So let's suppose if I want to know how actually your air is behaving over a body of any kind of body, right, surface of a body which is moving through the air. So let's suppose I consider a simple case of geometry is a circular cylinder. So it is a circular cylinder, right, which is moving through the air. Air is coming like this, right? So air is having free stream pressure and free stream velocity, it is having density, and I am assuming that density remains constant throughout the flow field, or I can say it is an incompressible flow domain. So now I want to basically know how actually pressure is behaving over this object. First thing, from the boundary layer concept, whenever flow is coming, the point is going to strike over the object. That point will be called a stagnation point, or you can say the no slip condition will exist at that point, and immediately after that boundary layer formation takes place, and because of the boundary layer formation your flow will get attachment, and after certain period of time, or after traveling over certain length of a surface, flow will not have sufficient energy to stick over the surface, and it will separate. The moment it is going to separate, it will be forming some sort of vertices backside, that is not called wake region. Alright, so basically our idea is to identify the locations of separation point, as well as the area of wake, how to minimize that. That idea you will get from the pressure distribution of a particular object. So how to do so? If we look at the traditional way of experimentation where we are going to find out Cp, how actually we do that. So usually we used to mount this object inside a test section of a wind tunnel. We need a wind tunnel. Wind tunnel is a device which maintain a constant atmospheric pressure. right, or controlled atmospheric pressure in a given domain. That the area or domain where we are maintaining the controlled atmospheric properties is known as test section of the internal. So usually we mount this on the test section of internal, and over the surface we put the n number of static pressure ports. How will you do that? We will divide this surface into n number of points. So if we divide like this, like this, like this for the sake I am dividing it, so we'll get these kind of points right over the surface, entire surface, bottom and top. At the same symmetrical location you will have a point. One point you can put here, one point you can put here, or in between also you can put some points, right? So these all points, at this point you will put the static pressure ports, right? Ports are nothing but it's a tube kind of structure, right, that will suck the air. So when air is coming and it travels over the surface, right, so through these ports, right, these holes, air will go inside, and that tubing will be connected to the multi-bank manometer, right? So multi-bank manometer, so each location usually we measure the pressure, right, and by taking pressure as a reference, that is called atmospheric pressure, we find out the pressure coefficient at different locations. So if I say this point as 1, here I can find out CP1, right? Point 2 I can find out CP2, and so on, so on, so on, like that. Like 20 points are there, I can get CP1, CP2, CP3, right, CP4, CP5 and CP20, right? Let's go, 20 points are there. I got the 20 points. The moment you got the 20 points, now easily you can plot over entire length of the flow. So whenever I'm talking about entire length of the flow, is nothing but this is the length of the flow. If I circular cylinder, then this diameter is my chord length, right? Usually we define, or length of the flow. So the moment I know the CP values at different locations, right, by using this formula. So if I am writing CP1, that means at this first port what is the pressure value, minus P infinity divided by half rho. This thing is known to you because initial velocity is known to you, and density of medium and a pressure, free stream pressure, that you basically you are supplying. Only variable is this, that is called static pressure. So static pressure, different locations will be variable, and with the help of that manometers we are measuring basically static pressure, and by using this formula we can find out CP's values at different locations. Finally, if you draw it over like this here CP, and here the fraction of this drag, means not drag, this diameter. So what is the length of the fraction I am saying this x, any distance along this. So this I say x divided by d, this is known as fraction of chord length, right? So if I am assuming this circular cylinder as my airfoil, this is the chord length, so some distance of this, so I can plot now these points. So CP1, let's suppose one point is coming here, another is coming here, it is going like this, now going like this, whatever point. Similarly downside also, if I am getting like this something, now I can connect from this point, and I can connect point by point in this way, and I can get this point. So this top surface, right, this is the top surface. So top surface, this is a bottom surface, right? So top surface, this is negative pressure, here positive pressure. Like that you can plot the pressure distribution for any kind of geometry. It is just simple case of circular cylinder I assumed. We can take airfoil, and over the airfoil we can divide this many number of ports, and we can plot this pressure distribution. So this is pressure distribution. So what information basically we get from the pressure distribution? This pressure distribution is going to decide how much lift that particular foil or airfoil is going to create. That information you will get from here. If this zone is bigger, that is the negative pressure zone is bigger compared to the positive pressure, you will have more lift. If this zone is lesser than this, it will have less lift. Clear? In some cases both the zones will be symmetrical. In that case it will be lying like horizontal. There's no incremental lift, right? This is the very thing. So more larger the negative pressure, more will the lift generated over the foil, right? So the basic idea is you got to know, right, in what side pressure is acting. So now when you are calculating the lift, you will take the pressure difference between top and bottom support. You can see you will take the pressure difference perpendicular to the flow direction. So flow direction is like this. Now perpendicular to that pressure difference, if you take a pressure difference is coming upward, you will have a positive lift. If it's coming downward, it will have a negative lift, right? When you are talking about drag, drag will be acting in the same direction of the flow. So if you are taking the pressure difference between front and back of this, pressure distribution, that will give the drag. The sideways force also can be, calculated front and back, this side and that side. If you measure the pressure difference in three-dimensional domain, that will give the side force. So like the different aerodynamic forces, easily you can calculate if you know the pressure distribution. That's why pressure distribution is very much needed when you are doing any kind of aerodynamic study over any kind of object. Is that clear? So this is the first point that I was thinking to discuss with you. Already we have covered this pressure distribution somewhere else. So let's start our next topic, how to calculate the drag and lift over the more streamlined body that usually we consider the airfoil. So how to calculate that mathematically? We know the definitions. Now we have to see. So drag and lift over a submerged body. Submerged body means if airfoil is traveling through the air, it will be fully submerged in the air. So let's suppose this is an airfoil. This is an airfoil, alright. So airfoil is having chord length. So this is the chord length of it, alright. And airflow is coming from this direction, right, in this way. This is the free stream velocity and this is the free stream pressure. So this is horizontal. If I draw a shortest distance between leading and trailing edge connecting like this is known as chord line, right? So angle made by the free stream flow direction. If I extend this, right, and free stream flow direction is coming like this, angle between the free stream flow direction and chord length is known as angle of attack. So this is my angle of attack. Is it visible? Angle of attack. So this is the angle of attack. Now for the sake of understanding, I consider here the center of pressure. This is the location of center of pressure. Center of pressure is the point at which resultant aerodynamic force is supposed to act. So the CP. So this is CP. So lift will be acting perpendicular to this horizontal line. So perpendicular to this is the lift, and the drag will be acting parallel to this. So this is the drag. A resultant of these two, if I take the resultant, this is known as resultant aerodynamic force. This is lift. This is drag. Clear or not? This is lift. This is drag, and this is the angle. Usually this is what is alpha you are getting. This alpha angle is also present here. So let's suppose I am taking one what we say elemental area over the top surface. So I have considered elemental area. This I have just drawn the test, this kind of thing. This elemental area is, let's suppose it is elemental area dA, which I have considered for the analysis of pressure distribution and shear force. So whenever any object is moving, so it will be experiencing two kind of forces. One is pressure force, right? Another is called shear stress. Why shear stress come into picture? Because fluid domain is having viscosity, and viscosity will resist its motion, and viscosity will contribute to the shear stress. So aerodynamic force is the combined effect of these two forces, pressure forces and shear stress, right? Shear forces. So as a result, you will get the aerodynamic forces. Now based on the direction of the flow, basically we see what is the contribution of which kind of force. If we are talking about lift, in lift basically shear force will have negligible contribution, but in drag definitely shear force will have more contribution because shear stress act in the direction of the drag. So it will dominate particularly in the calculation of drag, but in the calculation of lift there will be negligible contribution of shear stress. Now we have to relate in what way these are related. So that's why I have considered one elemental strip here, which is having area dA. So if I extend this line like this, I have extended like this. If I draw a free stream flow direction, this is here horizontal. It's basically a horizontal line. So if I draw like this horizontal line, this is a free stream flow direction. So the striking point is angle theta. It is making a deflection angle theta with the free stream flow direction. This is a free stream flow direction, right? Basically. So V infinity. So if I want to draw this right here, and then I will consider only two forces: pressure forces and skin friction or shear forces. So if I take this elemental area here, so I am drawing here. This is my elemental area which I consider for my study. So this is dA basically. So the pressure always acts perpendicular to the area. So this is the pressure which is acting here. So P into dA is the pressure force, right? P into D is the pressure force. This is a pressure force. So if I draw horizontal line perpendicular, this angle is also theta. right? And if I extend this area, if I'm extending this area like this, and if I draw a horizontal line here, this is theta, like I mentioned there, this is also theta. So the cos component of this will come like this, perpendicular to this. This is called P cos theta dA. Whether it is visible? Yeah. So if it's not visible, I will draw it slightly bigger, then it will be understood. So this is the elemental area which I consider for my study. So this is dA, right? If I extend this slightly this side, extend this, if I draw a horizontal line, this is theta, similar like this theta, and pressure acts perpendicular to this, right? This is my elemental area basically. So this is my pressure force P into dA, right? If I draw vertical line like this, right, like this, so basically this is making an angle of theta, it's making an theta, right? So that means what, if I draw the horizontal component of this, that will be what, P cos theta will be like this, right? This is P cos theta and this will be P sin theta. So if I take like this, so this force which is acting here perpendicular, sorry, so this force, right, which is acting like this, pressure force, it's acting like this, is nothing but P sin theta into dA. Clear? No, P sin theta, P cos theta, it's not sin theta, cos theta, cos component, right? Cos theta into dA. And the pressure force acting horizontal direction from here is P sin theta dA, right? So this is a P sin theta dA, this is a P cos theta dA, this is a P dA. So pressure force I have mentioned. Now what about shear forces? So shear force will act parallel to this direction. So this is here, this is the shear force direction. So I have mentioned here, this is the tau naught into dA. This is the shear force, shear force. Clear? This is the shear force, that is tau naught into dA. Tau naught is shear stress, right? Shear stress is force by area, shear force by area. So shear force is equal to tau naught into dA. D is my elemental area which I have considered for the study. This is my elemental area up to here. This is my elemental area. So now this is tau naught dA. So if I draw vertical from here like this, right, this is acting in this direction basically. This is acting in this direction. So one component will be acting in this direction, right? That is called tau naught, right, sin theta into dA, and in this direction this force will be tau naught cos theta dA. So I have mentioned the pressure forces and these are the shear forces, and one shear force was acting like this, right? Flow is happening from this direction, right? So shear force acting in the direction of the flow. So this direction was the initial and this direction is tau naught dA shear force. So one component of this is this, right? Another component is this. So tau naught cos theta and this, and P sin theta, P cos theta. Now we will write the elementary lift and drag equation. When we talk about elementary lift, so we have to consider all the forces perpendicular to the flow direction. So resulting the forces perpendicular to the flow direction for a lift. So dl, if I am writing, so if you look at dl, when you are talking about dl, so this is tau naught sin theta, dA is one term. Another, you look at, this is going down, so I can consider in this direction negative, right? P cos theta into dA. So this is the elementary lift. This is equation number 1. When you talk about elementary drag, right, so I have to resolve the force now parallel to the free stream direction. So first term is this tau naught cos theta dA, and also this is adding P sin theta dA. So this is equation number 2. So this is the lift, right? This is the drag, elementary lift, elementary drag. So now we know over here, so we can integrate over the entire length to get the overall lift and drag. So total lift, total forces, right, that is lift is equal to integration of dl, right, and total drag is integration of dd between 0 to c, right, chord length. Along the chord length you are basically going to integrate that. So going to integrate that, keep in mind. now thing is that see lift always be actually integrate between thickness, and lift is acting like this and drag is acting like this. So 0 to C is this and 0 to T or thickness is this. We can integrate and get the lift and drag. So now B will write, as we know there is a very less contribution of shear force in the lift. So we can write very simple equation here. So I am erasing this thing and I can write here simply two equations out of this. One is total lift is just simply integration of minus P cos theta dA. This is my lift, right? And drag is basically is a combination of these two, right? So P sin theta dA plus integration of tau naught cos theta dA, right? So lift is entirely due to the pressure forces acting perpendicular to this component we are considering, perpendicular to the flow direction. So we will take the pressure perpendicular flow direction. So along the thickness, what is the pressure distribution that we will consider. So along thickness, and we will go along the chord length, and finally we will summarize. So when you are integrating along the thickness and chord length, just you mention 0 to C and 0 to C everywhere, and you will get finally lift and drag. So lift is clear, lift is due to pressure difference perpendicular to the flow direction. Now drag, we are having two components. So first component, this is due to the pressure drag. This is known as pressure drag, or we can say form drag, or we can say profile drag. All are same. Sometimes we say profile drag, form drag, or pressure drag is the first term, and second term, this is called shear drag or frictional drag, right? Or skin friction drag, right? Skin friction drag. So we are having two component in the drag. One is called pressure drag and it's called skin friction drag. So pressure drag further will have 2 or 3 different kind of things. Sometimes we used to say pressure drag is due to entirely shape of the object, right? And flow separation, because of that will happen. And skin friction drag basically deals with the boundary layer properties, right? Boundary layer properties and frictional effects, right? All things will come in skin friction drag. So total drag is a combination of these two, pressure drag and skin friction drag. So like that we can calculate lift and drag, right, over any kind of object. I have considered a very simple case of airfoil. In a similar way, you can apply this through the circular cylinder or something else. Now we'll see the application, right, how actually this can be applied to different kind of shapes. So if we consider a thin flat plate, first case, flat plate parallel to flow direction, So I am considering a flat plate which is like this and parallel to the flow direction. Flow direction is like this. So flow direction is this. So here boundary layer formation will take place. Similarly here also it will take place. So along the along the length there will be shear stress, right? Shear stress, and this is the total chord length of this thing. And if you are considering delay and pressure will be acting like this. This is the pressure which is acting up and down. So here if we look at the flow deflection angle is 0. If theta is going to be 0, in that case what will happen? Lift will be entirely due to the pressure, right? Simply cos 0, that is 1. So P into area. So area is basically this total area that you are going to consider. This is the area. So if I say this is dA, so this is the total area that you are going to use, right, to find out the lift. So lift is simply minus P into A, and you can find out. If you look at the drag, so drag will be entirely due to the skin friction. In this case of thin flat plate parallel to the flow direction, there will be only one component of drag, that is called skin friction drag. So this is skin friction drag, that is represented by dF, is nothing but tau naught, right? Cos theta is becoming 1 cos 0 into dA. Right, so this is the skin friction drag, and sometimes same half rho V square, right? Half rho S is the area, right? Or you can just write A into CDF. This is the coefficient of skin friction drag. CDF is the coefficient of skin friction drag. Half rho V square dynamic pressure area. You can get the skin friction drag. So in a flat plate, when it is parallel to the flow direction, there will be only skin friction drag. There will be no pressure drag. now consider the second case. Second case when this plate is perpendicular to the flow, right? So when it is perpendicular to the flow, second case we are considering flat plate perpendicular to flow. That's the second case. So in this case, what will happen? This is the plate which is facing the flow, and flow is coming from this direction. So it comes here, right, and strikes over here. First stagnation point we got here, right, and after that it travels like this, and at this edge it starts separating. Similarly, flow comes like this, right, and comes over here, and from here it's separate. The moment it's separate, it will be creating this kind of vertices. This is called wake. So along this is the another stagnation point, right? So S2 we can say this is S1, this is S2, right, and along this direction, right, the shear stresses will be acting both this direction. This is shear stress, and pressure will be acting like this. This is the pressure, and pressure from this side. So if we look at here, flow deflection angle become theta is equal to 90 degree. If theta is equal to 90 degree, lift, we will not get any kind of lift. Basically it's directly hitting the surface directly, flow is getting separated from top and bottom. Lift is going to be zero, so we are not going to get any kind of lift. So lift is zero. Only there will be drag, and that will be very big contribution of drag, that is called pressure drag. So sin 90 is equal to 1, we know. So this is the pressure drag, and area if you look at wake area is bigger. So if my flat plate is facing the flow at 90 degree, it will generate larger amount of drag, that is called pressure drag. So there will be pressure drag dP. So dP is simply 0 to area you can find out, and P dA. So this is known as pressure drag. This formula is also similar, half rho infinity V infinity to CdP, where CdP is the coefficient of pressure drag, So like that we can find out. So we have seen that if my this thickness is less, I will have lesser drag, that is only skin friction drag will be present. If the thickness is bigger, I will have pressure drag, and pressure drag contribution is more compared to the skin friction drag, right? So if we compare three bodies in a similar way, right, now I am going to compare three bodies in a similar way, in which case we will have which kind of thing. One is the thing which we have got like this, right? So in this case flow was coming like this and getting separated here. It was coming like that and separated from here. So here large wake region is present. This is a flat plate, right? Flat plate perpendicular to flow. Second case, you consider circular cylinder, right? Is a circular cylinder, flow is coming like that. First stagnation point you will get here. Now flow will go like this and travel up to here, and goes like that and travel up to here. If you look at here, some wake formation will take place. So this is a cylinder case. And now you consider more streamlined body. If I say airfoil is more streamlined body. So in this case, airflow will come, it will travel over large length and separate, right? And similarly, it is coming like that, it separates here. So if you look at here, wake formation area is very less in the case of airfoil. So if we consider here, in first case pressure drag is more, here pressure drag is slightly lesser than this, here pressure drag is almost negligible, but length is more, so skin friction drag will be more. As viscosity of air is very small, so skin friction drag will have very minute contribution in total drag. It may be only 0.5% of the total drag. So that's why we prefer airfoil kind of shape. So if we talk about total drag, right, so total drag in first case D1 will be bigger than D2 and bigger than D3. So D3 will have a smaller contribution. This is the first case, second case and third case. Clear? So smallest drag we are getting in the case of airfoil. That's why we always talk about streamlining of the body. This is a fully streamlined body, right, which will create a very lesser amount of drag, right? This is the one thing. So this is the second topic that we have covered. Let's go to the third topic. Let's see how many types of drags are present. So this is over, right? So in a similar way you can I expressed here, for lift also you can write some equation we will later derive. So lift is also given by half rho V infinity square area into CL. This CL is known as coefficient of lift. A is called planform area, and this is the dynamic pressure. Similar way, and we will derive this by using dimensional analysis in the next chapter. So we stop discussion of lift and drag here. Let's go to the type of drag or types of drag. So drag is something that we are paying for generating lift, right? So this is the cost basically we are paying. So drag, how actually it happens? So drag happens due to various factors. Till now we have seen that due to the shape of the body, and due to shape of the body there will be various kind of flow geometry changes. Because of that drags may occur. And second condition, based on the location in which your object is moving, based on that also your drag will be properties will be entirely different. So that's another parameter. And yes, so basically total drag is having two contributions, right? First is due to pressure drag, another is skin friction drag. Skin friction drag is very negligibly small, sometimes we neglect. So majority of contribution is from pressure drag. So pressure drag will have different kind of forms. Let's see, discuss one by one. So take first case of drag, that is called viscous drag or skin friction drag. Skin friction drag. This is a very common drag. So viscous drag occurs due to the viscosity of the air. So what is the viscosity? Viscosity is the property of fluid by which it offers resistance to the motion of its layer, or shearing is of layer. So it occurs, viscosity basically happens between the layers, so it will resist the motion of one layer of fluid to the another layer of fluid. So its drag due to this viscosity is known as viscous drag. So as I said, between the layers there will be velocity gradient, right? So if layer is very closer to the surface, it will be in a state of zero velocity, or you can say it will be in a state of no slip condition. If you are moving away from the solid surface, there will be difference in velocity between layers. So velocity gradient exists between layer, and which kind of velocity gradient will exist? So if it is a solid surface, so if you are going away from the solid surface, we will get this kind of velocity gradient. So here velocity gradients are taking, these are different layers. So if you are going away from this at solid surface, velocity is zero, or you can say no slip condition, this solid surface, right? If you are going away from here, it will be parabolic up to certain height. After that it will become free stream velocity again. So the effect of viscosity will be negligible, means completely zero at this height, right? Below this there will be a change in velocity, right? So as you are moving towards the solid boundary, our velocity is keep on decreasing. If you are moving away from the solid boundary, our velocity is increasing, and after a certain time it becomes the maximum positive velocity or free stream velocity. Alright, so this is known as velocity gradient. So when we are talking about velocity gradient, let's suppose this is the y direction, right? So change in velocity is du. So velocity gradients I can write du divided by dy. Change in velocity in y direction, this is known as velocity gradient, right? Or rate of shear strain, you can say. So shear stress is directly proportional to rate of change of strain. So when you remove this directly proportionality constant, you will get one constant mu du by dy. This mu is known as coefficient of viscosity. Sometimes we say this coefficient of viscosity, or absolute viscosity, or dynamic viscosity. So when we are talking about absolute viscosity will be defined if fluid is at rest. If fluid is moving, we will say that is a dynamic viscosity. But there is no basic difference between that. It will have same notation, it will have same values. Alright, it depends on the domain. Domain is moving or domain is stationary. If domain is stationary, we will say it's absolute viscosity or coefficient of absolute viscosity, or if its domain is moving, we'll say dynamic viscosity. And because of this, whatever force is acting, that is called drag force. So when you are talking about drag force, this tau is nothing but F viscous divided by area. Alright, so I can say frictional or skin friction force or drag, sometimes we say dF is also correct for this. This is nothing but tau into area. And which area? Basically this area is surface area. Basically it will be taking surface area of the plate, pi dl for in the case of circular cylinder, or length and width that you consider. So the area is surface area. This is called as frictional drag. Or in a simple way you can write half rho infinity v infinity area into CDF, where CDF is the coefficient of skin friction drag. So this is the first kind of drag. Now second kind is first is skin friction drag is over. Next one pressure drag. So pressure drag occurs due to the shape of an object. So if object is moving, right, so pressure drag occurs due to the pressure difference between the front facing flow and rear flow. If you take the difference of between these two, that will give the pressure drag. So as I said, if my plate is moving like this, it will have more pressure drag because this side pressure will be more, all of a sudden pressure will be less. Also it will resist the motion of the object, right, motion of the object. So pressure drag will be more in this case. If I am keeping like this, right, in this case pressure will be less because less obstruction to the flow. So basically the pressure drag depends entirely on geometry of the object, and it can be minimized by making your geometry more streamlined, right, more streamlined. That is known as pressure drag. So things are very simple. It's due to geometry. This is also known as profile drag. This is also known as profile drag. So if I am considering this case 1 and this case 1, in this case, you know, flow will get separate like this. Right, in this case flow will be at least traveling and then it is separating, right. So we will have this much range of what we say wake region. So in this case, if we say coefficient of pressure drag is 1.4, here CDP will be only 1, right. So look at the coefficient of pressure drag. In the case of circular cylinder, just 1, right. So compared to this shape, rectangular shape or square shape, pressure drag will be less in the case of circular cylinder because this slightly streamlined compared to this. There is no sharp corners present. So we have to avoid the sharp corners so that flow should adjust very smoothly over the surface. So if there is more flow obstructions, more will be the pressure drag, right. This is the second case. Third case is induced drag. This is very, very important, right. Induced drag. So induced drag basically occurs due to the trailing edge vortices, or you can say those bakes which are forming at the back side. Because of that, whatever drag is creating, that is called induced drag. So why we say this is induced drag? Because it will induce a downward component of velocity, right, at the back side of the object. So if I say this is an airfoil which is traveling, right, like this at a certain angle, so flow comes like that and separating from here. This is the case. So here you will get this kind of vortices which are forming. So vortices, they will induce a downward component of velocity, that is called VI, induced velocity. What the downward velocity component will do, it will try to push your tail down. If your tail is going down, what will happen? Airfoil will lose the altitude. When it is going to lose the altitude, its velocity will also get affected. So the motion by which it was traveling will get obstruct, or you can say it will provide some braking action over the movement of the airfoil, and that type of drag is known as induced drag. And we need to avoid this kind of vortices at the trailing edge, right, by making your trailing edge shape changeable, or by energizing the flow at the trailing edge so that there should not be any separation near the trailing edge, right. In previous chapter I discussed about boundary layer suction device or blowing device. Those can be employed to re-energize the boundary layer. So the drag due to the trailing edge vortices is called as induced drag. It will induce a downward velocity component. So that drag is known as CDI is equal to KCL square, right, or you can say 1 upon pi ER. K is y pi r CL square. So CL square upon pi ER is known as induced drag, right, where E is known as Oswald efficiency factor or wing efficiency factor, and this is having very narrow range. Usually it will be 0 or between 1. So any value between 0 and 1 we consider as Oswald efficiency factor. For most of the wing it is 0.9 or 1, right. Usually we consider 1 always. And R is known as aspect ratio. R is aspect ratio. Sometimes we say this is AR. Some books are using AR. Aspect ratio nothing but wing span divided by chord length is known as aspect ratio. So pi ER and CL square, coefficient of lift, right. So vortices, how vortices are producing basically? Vortices are the result of lift basically. When we generated the lift is generated to the circulation. When circulatory flow comes at the trailing edge and when it's going to separate, they will be generating the tip vortices. So induced drag is the cost basically for generating the lift. We have generated the lift, because of that trailing edge vortices form, and that trailing edge vortices will induce the drag that is called. So drag due to lift is known as induced drag. That's why CL term is there, right? So this derivation is not the part of the syllabus. If you are interested, I can put one derivation for you in this case. That will derive basically later on. So this is the third kind of induced drag. If you go for fourth type of drag, that is called wave drag. Wave drag. WAVE, wave drag. This type of drag forms basically at very high speed when your object is traveling at Mach number greater than 1. When it is crossing the Mach number greater than 1, there will be formation of shock waves over the boundary of the object. So drag due to the shock waves are nothing but compression wave. So all of a sudden your flow properties will change. Initially it will have some value, finally it will have some value. Sometimes velocity initial will be more and final velocity is going to be completely reduced. And that is the case, means all of a sudden your object will be experiencing abnormal flight conditions, and that kind of drag is known as wave drag. So wave drag is nothing but drag due to the formation of shock wave. Usually it will occur at very high speed, Mach number greater than 1. So this is a wave drag. Next is aerodynamic interference drag. So the term itself is saying interference, right? So flow over one body, if two bodies are going like this parallelly, flow over one body disturbs the flow over another body, and due to this disturbance, what will happen? It will contribute to some sort of drag over the object which is nearer to it. Let's suppose two aircrafts are passing way. One is going like this, another is going like this. So flow over this aircraft will disturb the flow over another aircraft. So all of a sudden, second aircraft will feel unstable because of the interference between these two aircraft. That's why two aircraft, when they are passing, they used to keep a lot of difference around. They used to keep 200 feet distance between each other. If they are closer to 100 feet, even 100 feet, the second aircraft will experience a lot of disturbance due to the airflow interference, right, between two planes. So that's why lot of spacing is required when two aircrafts are going to passing away. It's not like land-based application, one truck is going and another truck is moving parallel to it. It's not getting destabilized because between the truck interface drag is very less, right? Because when we are traveling at in the air, aircraft will be traveling at 900 km per hour, maybe 800 km per hour. The speed is very high, so airflow around the object will be traveling at a very faster rate. If another object is coming near to it, it will destabilize completely, and chances are there another aircraft may crash. That's why we keep that much distance. So in the case of aircraft, interface drag is more. In the case of land-based application, it is less. That's we do not feel. But if you are going on a bicycle and some truck passes nearby you, you will feel the destabilizing force over you. That is called interference drag. So aerodynamic interference drag, right? Next one is cooling drag. Cooling drag. So why cooling drag comes? The name itself is cooling drag. So in the aircraft, basically we are not storing any air inside, right? We are taking air from outside. So outside air temperature is low. So we take outside air to cool the different parts of aircraft engine. So aircraft engine will be subject to very high temperature environment. So to cool that, we used to take atmospheric air and we pass that air over the various component of the aircraft, and that will also contribute to the drag because air will have viscosity, and viscosity will contribute to skin friction drags, right, and drag, and that will contribute to that drag due to those movement of free air on various component of aircraft or compartment is known as cooling drag. Even though it will have very negligible contribution in drag, but it is a part of drag, right? When you are calculating total drag, even 0.01% of total drag will also have a meaning in performance calculation. So this is known as cooling drag. So if we next one is a parasite drag. Parasite drag. Drag due to the surrounding parts of an aircraft wing. So if it is an aircraft will have different kind of surfaces. Ailerons are there, right? Spoilers are there, vortex generators are there, and elevator is there. So drag due to those all movable parts, right? So drag due to the surrounding parts of an aircraft wing is known as parasite drag. So parasite drag is negligibly small. So sometimes parasite drag and pressure drag or parasite drag and profile drag together known as profile drag, right? So if you take the contribution of this parasite drag, maybe 0.3% in the total drag. So we usually consider this parasite drag as a part of form drag or profile drag. So profile drag and parasite drag together known as profile drag. So these are the different types of drag. So when we are talking about total drag, so total drag, that is D, is nothing but profile drag plus induced drag, right? Profile drag and induced drag. So all these aerodynamic interference, cooling, wave drag, and pressure drag will come here. So this is known as a profile drag. Profile drag. Why is saying profile drag? This is happening to geometry, right? Geometry. So these all drag depends on the geometry of the object which is traveling at that environment. Interference also depends on the geometry. Shock wave formation also depends on geometry. So due to geometrical features, what are the drag? There is a profile drag. And second is induced drag. Induced drag. So induced drag is this. So if look at this contribution, right, this profile drag will contribute to 15% of the drag. Usually when we do the calculation, you will come to know. So 15% contribution in total drag is due to the profile drag, and rest of the 85% contribution in the total drag is due to the induced drag. That's why we used to say avoid the trailing edge vortices, make some arrangement, avoid the trailing edge vortices. How can we avoid? By avoiding the separation, early separation on the top surface, by energizing the flow by any means, right? Use any method to energize the flow and make your flow turbulent so that it leaves the trailing edge very smoothly. So at the end you will have very less amount of vortices present. So 85% is in the total drag is due to induced drag and 15% this. So if we write in coefficient of drag, this is the coefficient of drag, this can be written as CD naught plus CDI, or this is CD naught plus KCL square, right? KCL square. This induced drag due to the lift, and this K is nothing but K is a coefficient, that is 1 upon pi E AR or just R, right? This K is here. So coefficient of drag is profile drag coefficient plus induced drag coefficient. This is known as total drag. Is that clear? So like that we do the calculation of total drag. So today we have discussed about the pressure distribution. We have seen how pressure distribution is important, right, to find out the aerodynamic forces, and we have developed a relationship for lift and drag, and we have seen the example of lift and drag over different kind of geometries, right? And finally we come to the conclusion that streamlining of object is much necessary for the vehicle which are traveling through the air, right? That's why all the parts which are exposed to the outer atmosphere are usually curved one in the aircraft. You see why I'm making curved one. We don't want any sharp corners. Sharp corner will contribute to large amount of drag. So that is called streamlining. And then after that we have discussed about pair-based kind of drag, where we have discussed seven categories of drag, and finally we have find out the total drag. The total drag will be calculated like this. With this I am closing the today discussion. If you are having any doubt in this topic, please feel free to approach to me. Either you can write in comment section, or you can contact to me via WhatsApp. So thank you for listening to today's lecture. Have a nice day. Good day.